So now we come back to our primary question. Again, how do we encode L systems in Python? And we've done with our step 1, which is we discussed the relationship between images and symbolic schema. So we move on to step 2, where you have to write a Python code for the symbolic schema that we developed so far. So how do you really write the Python program? So there are some 3 questions that come. So how do you represent strings in alphabets? How do you encode the rules? And how do you encode iteration? So how do you represent strings? So we need to make a couple of observations. So observe that alphabets are just regular keyboard symbols. That's A plus F minus, right? I mean, they're just like some keyboard symbols that you have. Words and strings resemble symbols put together in an order. And what you need to remember is list contains symbols put together in an order, right? So if you remember this fact, then we realize that automatically lists are your natural choice to represent words. So words and strings can be represented by lists. So for instance, AAABB can be represented like this. So how do we encode rewrite rules? So observe that rewrite rules take a string as an input and return a string or a word. And what you need to remember is that this actually resembles the structure of a function, where a function takes an input and returns an output. But in a rewrite rule, you have a different output to every input. So what we can actually use are conditionals, which actually model an output depending on the kind of input that you get. So a broad structure of this rewrite rule is given on the left side. How do you actually write a rewrite rule in Python? So it's a function which depends on one variable. Now if x, depending on the value of x, it returns the word corresponding to the value of x. You see a broad example here, and you use conditionals to kind of mark them out and separate them. And when you have no more conditions left, you can always use an else. Right? And on the right side, you see an illustration of this. So for instance, if x is A, you can return A, B, A. Else, if x is B, you return B, B, B. Else, you just return the term x, except that x is no longer just given back as a word, but it is given back a list containing x. Because the output of rewrite is always a word and not an alphabet. Right? And it's important to note that a list containing an alphabet is different from an alphabet in terms of Python types. On the right, you see an illustration of it, and you can actually use it from the kind of broad definitional formula given on the left-hand side to write more and more rewrite rules. So in encoding rewrite rules, you also have to observe that rewriting a string is different from rewriting an alphabet. Because for an alphabet, you just have a simple rewrite rule, but to rewrite a string, you need to use what we call parallel rewriting. That is basically you have to rewrite every alphabet simultaneously. So how do you do that? So you have this definition function that we write called par_rewrite, which attempts to do that. Now what this par_rewrite does is it acts on this list ls, which is the word that in question that you have, and how it acts on it is if the list is empty, it just returns back the same list. But if the list is not empty, then what it does is first it looks up this dummy variable we have called QS, which is an empty list. And now you actually parse through the list. And at each point, it rewrites the alphabet of the list that you have, and corresponding to the alphabets, it gives out the word, and that word keeps getting added to QS. And now, since it keeps getting added to QS primarily consists of the word in which each alphabet is rewritten. And so it returns back the list, which is basically the list ls that's rewritten under parallel rewriting. So this is what par_rewrite works. An important point to note again here is that we actually use rewrite itself here as a variable in the function. So one of the things what it enables us to do is that it does not make us loyal to any one particular rewrite rule. So I can define 2 or 3 different functions called rewrite 1, rewrite 2, rewrite 3. And as long as I can pass those functions within this as a variable, and for each rewrite rule, I can just use this function by just replacing this term again. So I don't need to really write a new function if I want to do parallel rewriting with a different rewrite rule. This one function can actually suffice for multiple rewrite rules. So how do you program the iteration? And that is basically the missing step here, that we want to program the iteration. So iteration, if you remember, just follows a recursive structure. So what we do is we take a word, and to each word we just keep applying the same rule again and again. And for any nth word is basically obtained by actually applying the rule to the n-1th word, right? So to each string previously obtained by iteration, we apply the iteration again to obtain the successive string. So that's how you actually get back your new words that are generated in your L systems. For instance, here we've written the function. So the important variable here to note is n, And n basically refers to the number of times you're actually iterating it. And remember that your iteration also depends on your input, which is given by the axiom here. So axiom refers to the variable, which is your input. And rewrite, again, like the last time, we just wanted to make it more and more flexible to kind of have it for different rewrite rules. So we just apply the rewrite here. So now if your n is 0, it just returns the input, which is basically your axiom. Otherwise, what it does is it returns the slightly more complicated term, which is basically essentially recursive, because you can see that we've called iterate again here that you've seen, which is basically just the name of the function. So what does it really do? So this term that iterate, it iterates the input word n minus 1 times. So using the rewrite rules, you just write your input word n minus 1 times. Okay. And after you rewrite it n minus 1 times, you do a parallel rewriting on the word, which basically kind of, when you recursively, so at each point it does parallel rewriting and it keeps iterating it again and again. So that's essentially what your iterate function works. So now we really developed a Python code for the symbolic schema, because we have both our rewrite rules, our strings and words, as well as our iteration schema. So now what you really need is a Python interpreter for these rules. So which basically we have to convert them back to Python and geometrically be able to generate these rules. And of course, for this purpose, we choose what we know best, which is total. So how do you really write your total interpreter? So the step 1 of writing a total interpreter is you write an interpretation for each rule. Okay. The step 2 is write an interpretation for each string. And observe that iteration of a still is still a string, and this is important because you just need to write one interpretation and then it can even serve for the iterated string itself. So the first step is to write an interpretation for each alphabet. So for each alphabet, you have to assign the corresponding total function which performs the geometrical action associated with the alphabet in the L system. So for instance, here we write this interpreter function on the left side, which takes this variable x. Now, and how we kind of write it is, if x is a, the turtle moves forward by 30, or if x is b, turtle just draws this blank line of 30. So the general broad pattern is you basically take your variable x, and now depending on the value of x, which can be assigned using the conditionals, you perform the corresponding turtle action. So that's broadly how you would write it for a more general case, and you can adapt it to the kind of cases that you would want to do it. And now we have an interpreter for a list. So once you have an interpreter for each symbol, then you can actually have an interpreter for a list. So what it does is it parses the given list, and by using the interpreter function, it executes a total action corresponding to the each alphabet here. So given an interpreter rule, you have an interpreter function. So once you have an interpreter for each alphabet, you can also have an interpreter for the larger list itself. So what it does is it just parses the list, and think of this list as a list of instructions. So at each point in the list, it carries out the instruction that is now prescribed. Okay. And how it really converts this instruction is basically, so each point the symbol is converted to an explicit tuple instruction by the interpreter function, and now Python just carries out these instructions. So for instance, here you can see how the function is written. Your list interpreter is that if your list is trivial, it just moves forward by 0, which means it does nothing at all. Else, it goes through the whole list, and at each point in the list, it basically executes the action that corresponds to the alphabet in the list, and that is given by the interpreter function. So now how we actually put these two pieces together is that, one, you iterate the list for n number of times, and then you interpret the iterated list to obtain the iterated picture. So for instance, you have this list underscore interpreter, rewrite an axiom. This is the most broad general way, and a very specific case could be that I use my rewrite rule as rewrite. I use the 10 as the number, and I can write my a as the axiom, the word, and voila, we're done, because this is all that you really need to actually generate your iterated L systems. So this is a demo. So as you can see the program here, you can actually start off by the usual things of inputting total and naming the total, and then we just set the total at a nice enough distance so that we don't start always from the center. So you have your rewrite rule, you have your parallel rewrite rule, you have your iterated function, you have your interpreter and a list interpreter. Okay. And then we execute this command where we iterate it one time and see what the total does. So as you can see, if you iterate it once, it just like draws these two red lines with a green line in the center. Now I just change it to iteration twice. You can see that it kind of corresponds to the figure that we saw before. And now if I iterate it thrice, so if you iterate it thrice, you can see a much nicer figure as you see here. And so you have these shades of red, like large spaces of green in between, and you have shades of red and green. So what really one way of interpreting this symbol structure is at each point you just take out the middle 1/3, and then from the rest you keep taking out the middle 1/3. So it could be like seen as a one-dimensional analog of the Sierpinski triangle, and mathematicians are often interested in something like that, and it is basically what they call the Cantor set, and those of you who might study mathematics further would encounter it at some point. So we go back to our code and we observe the following things, that only the following functions depend on the specificities of L systems, that is rewrite and interpreter. Only they depend on the kind of L system that we're really talking about. So list interpreter can be made independent of the interpreter. Of course, if you notice that list interpreter, the way we use it depends only on the list and not the interpreter, because we assume that the interpreter is already given. So it can be made independent of the interpreter by passing the interpreter as a variable. And you can do it just like the way we wrote rewrite as a variable inside of iteration. So to generate new L systems, all we need to do is to rewrite the new rewrite and interpreter functions for the L system and pass them through the appropriate functions. So you can just rewrite your functions again, and you can use your interpreter again and just pass them. So for instance, you have the Sierpinski triangle that you see here. You have this generating rules which are given by 4 symbols f, g, plus, minus, and an axiom f minus g minus f, g, and you have a set of rules, and your interpretation is f, g are just forward by constant length, plus is turned left by 120, minus is turned right by 120, and you can generate your Sierpinski triangle. Now if you want to actually generate your Sierpinski triangles, it's basically largely the same code, except that we've added 2 new functions to the list. So again, I'm just reusing the same code itself. I don't need to write a separate program for this. So I just add a new rewrite function and I add a new interpreter. So in this new interpreter, it basically kind of corresponds to the interpreted rules and the rewritten rules. So for instance, in the interpreter here, if x is f or x is g, it basically moves forward, otherwise it moves left or it moves right. Of course, and another important difference I made is now list underscore interpreter depends on the interpreter. Interpreter is no longer just a constant, but it basically can vary with the kind of interpreters that you're using here. So now I have my list underscore interpreter here, and I just pass the same function again. And here the value of interpreter that I'm taking is interpreter underscore s, and the rewrite rule that I'm considering is rewrite underscore s. And then I run this code, iterating it 3 times from starting from the initial word that I've specified. And as you can see, it kind of gives me a Sierpinski triangle. So as you could see, we just kind of elaborated on the functions that we've changed here. That's all one needs to change, and we kind of write a list underscore interpreter in this fashion. So some exercises for you. These are pictures that you can find on the Wikipedia page for L systems. So you can go look out the rules for it, and you have to kind of draw the corresponding L systems by changing and tweaking the code that you just learned in the class. And if you really liked this topic and you want to look more, there's this lovely book by Lindenmayer himself, L in the L systems, if you noticed, was stand for Lindenmayer, and it's a beautiful book called Algorithmic Beauty of Plants. So thanks for all the attention and have fun.